Hi, today we're going to talk about two different ways to calculate free energy reaction under standard conditions. As a bonus, I will also give you a way to calculate the free energy of reaction at a non-standard temperature. So there are two ways we can calculate standard free energy, and they both involve using the thermodynamic tables that you find in the back of your textbook. The first one is to calculate your enthalpy of reaction and your entropy of reaction, and then use delta G equals delta H minus T delta S to calculate the free energy of that reaction. The second is to use the values in the thermodynamic tables for free energies of formation. So if you have the change in enthalpy and the change in entropy for a reaction, you can use that to calculate the free energy. First of all, we normally think of delta G equals delta H minus T delta S. This is our temperature. Remember that everything you're getting out of those tables is for standard conditions only, so we can only use this at the temperature of 25 Celsius or 298.15 Kelvin. Remember, we always put Kelvin temperatures into this equation. Then you're going to calculate the change in entropy from the table by plugging in the standard entropies from the products minus the standard entropies of the reactants. And for delta H, you're going to use the standard heats of formation for the products and reactants to calculate the enthalpy change for the reaction. That's something you should have learned how to do in Gen Chem 1. All right, so here we're going to practice that on this reaction, putting together nitrogen and hydrogen gases to make hydrazine, which is a gas that can be used for rocket fuel. So the question is this reaction spontaneous when we're at standard conditions? So we're going to calculate this by using delta G equals delta H minus T delta S, and we're going to need to calculate both delta H of the reaction and delta S of the reaction. So let's do that over here. We'll start with delta H. And remember, we're just going to do the heats of formation of the products, add those up, minus the sum of the heats of formation of the reactants. And so we only have one product, hydrazine, N2H4, which has a heat of formation of 95.4. Our heats of formation of nitrogen and hydrogen are both 0 because those are in their standard state. So that's easy math. It just ends up being 95.4 kilojoules per mole for our enthalpy change of the reaction. Now we have our entropy change. Again, the entropy change for the reaction is going to be the sum of the standard entropies of our products minus the sum of the standard entropies of our reactants. And so we have 238.4 for our single product. For our reactants, we have 191.5, which is from our nitrogen. We have 2 times 130.6 because we have 2 molecules of hydrogen gas in this reaction. We plug that into our calculator and we get negative 214.3 joules per mole Kelvin. Now, before we go through and calculate our free energy for this reaction, I want you to think about what we expect that free energy to be. Here we have a delta H value that is greater than 0, 95.4 kilojoules per mole. So this is an endothermic reaction. And so I want you to think back to the previous video where we talked about the conditions under which reactions like to happen. So an ideal reaction, one that is always spontaneous, is both exothermic and increases in entropy. So here we have something that's endothermic, that is not very favorable from an energetics point of view. And we also have an entropy change that is negative. So that's very unfavorable from an entropy point of view. So this is a reaction which is not favorable from the delta H standpoint and not favorable from the delta S standpoint. This should be something that is just not a spontaneous reaction. But let's take our numbers, let's plug them into our equation and see what we come up with. So I've taken those numbers we just calculated, I've plugged them in. Now, one thing I want to point out to you that a lot of people miss out on is that our units for our delta H are kilojoules per mole. Our units on entropy are joules per mole Kelvin. So we have kilojoules and we have joules. You have to convert one of those. Either convert the kilojoules to joules or convert the joules to kilojoules. I'm going to do the latter. And now we can just go through, stick it into our calculator, and we end up with a delta G value of plus 159 kilojoules per mole. Remember that a delta G value greater than 0 means this is not a spontaneous reaction, and that is what we predicted before we calculated it. Okay, the second way I said was to use the free energies of formation, which are found in the thermodynamic tables. So these work very similarly to enthalpies of formation, and you calculate them exactly the same way, where the delta G of reaction is going to be the delta G of the products minus the delta G of the reactants. So let's go ahead and do that for a reaction. This reaction involves calcium carbonate, also known as limestone, and HCl, which react to form calcium chloride, water, and carbon dioxide gas. Now, if you've ever taken a geology class where you had to identify minerals, there's actually a test called the acid test, which you use when you suspect that something is made of carbonate. And if you've ever done this, you know that if you put acid on carbonate, you end up getting it to fizz. That's the carbon dioxide forming. And so we know this is a spontaneous reaction because it happens without us needing to put any energy into the system. So here's our equation. And let's identify the things we need in the table. So we're going to need our products, and those are calcium chloride, water, and carbon dioxide. And then we're going to need our reactants, calcium carbonate and HCl. One thing I need to point out is be sure to multiply the HCl by 2 because you need 2 molecules of that. You should never forget to include the coefficients in your reaction. So if you add up everything within the square brackets, you get negative 1508.8 minus negative 1,470, and that works out to be negative 38.8 kilojoules per mole. So this is a spontaneous process, as we knew it needed to be. All right, now everything we've done up till now has been done at standard temperatures. And what we're going to do for the rest of this chapter, both in this video and in the next one, is we're going to talk about non-standard conditions and the relationship between non-standard conditions and equilibrium. What I'm going to do here is I'm going to talk about how to estimate delta G at temperatures that aren't our standard temperature of 25 Celsius. And basically what we're going to do, this is an estimation, but we're going to assume that the enthalpy doesn't change very much with temperature, and that the change in entropy doesn't change much with temperature. Now that is not as good of an approximation. We know delta S does change with temperature, but there is already a temperature factor built into our delta G equation that's going to help us compensate for that. So here's the equation we're going to use. Delta G at a given temperature is going to be your standard delta H minus your temperature, whatever that is, times delta S at standard temperature. So let's try that on a reaction. So here we have a reaction in which formic acid is splitting up to form carbon monoxide and water. And we have been given our enthalpy for this reaction, 72.4 kilojoules per mole. So this is an endothermic reaction, not favorable from an energy point of view. And we're given delta S of the reaction, the entropy change, that is 257.3 joules per mole Kelvin. So our entropy is increasing. So this is favorable from an entropy point of view. It's unfavorable from an enthalpy point of view. And if you remember what we said in the last free energy video, that means that whether our delta G is negative or positive, whether this reaction is spontaneous or not, will be dependent on temperature. So we're going to look at this at two different temperatures, at 25 Celsius, standard conditions, and at 0 Celsius. So here's the equation we're going to use. This is not an approximation because the first one we are calculating at standard temperatures. So we can just go ahead and plug in those numbers that we were given. Once again, we have the issue of having joules per mole Kelvin for the entropy and kilojoules per mole for the enthalpy. So I'm going to convert the entropy into kilojoules per mole Kelvin. And now we can just run that through our calculator. And we get negative 4.31 kilojoules per mole. So under standard conditions, this is a spontaneous reaction. Now let's calculate what happens at 0 Celsius. Here we are approximating. We're calculating the delta G at 273 Kelvin. And so we're going to plug in the same numbers we plugged in before. The difference is we're plugging in a different temperature. Everything else is the same. And again, I'm putting the entropy in terms of kilojoules per mole Kelvin. And if we run that through our calculator, we see that delta G is 2.12 kilojoules per mole. So we have cooled down the system by 25 degrees, and we've gone from a spontaneous reaction to a non-spontaneous reaction. So we've talked about two different ways we can calculate standard free energy changes. One of those is slightly easier than the other in my experience. And so you might ask why you would do one rather than the other. The answer is sometimes you cannot find the free energy of formation for a particular substance, and then you would have to do it the long way with the enthalpy and the entropy. We've also talked about ways to estimate free energy at a non-standard temperature, and this will be useful as we dive into our next topic on the relationship between free energy and equilibrium. I hope this was helpful, and I will see you again soon.